Introduction.
Good morning, teacher.
Good morning, students. Today we will learn about aldehydes, ketones and carboxylic acids.
Teacher, what are aldehydes?
Aldehydes are the organic compounds containing the aldehydic group at the end of a hydrocarbon chain. What is aldehydic group, teacher? Aldehydic group is a functional group defined as CHO. Now, can anybody tell me what are ketones?
Yes, teacher. Ketones are the organic compounds in which a carbonyl group is bonded to two carbon atoms.
Very good, Ritu. In this lesson, we will learn more about aldehydes, ketones and carboxylic acids. Objectives. At the end of this lesson, you will be able to define carbonyl compounds, describe nomenclature and structure of carbonyl group, explain preparation of aldehydes and ketones, explain physical properties of aldehydes and ketones. Carbonyl compounds. In organic chemistry, carbonyl group is a functional group consists of carbon atom double bonded to an oxygen atom. In aldehydes, at least one valency of carbon atom of the carbonyl group is satisfied by one hydrogen atom and the other valency is satisfied by carbon of an alkyl or aryl group. Thus, the functional group of aldehydes is CHO. In ketones, the two valencies of carbon of the carbonyl group are satisfied by carbon of an alkyl or aryl group. The ketones can be represented by the general formula RCOR-, where R and R- are alkyl groups. The compounds in which carbonyl group is bonded to oxygen are called carboxylic acids. The derivatives of the carboxylic acids are the compounds in which carbon of the carbonyl group is attached to nitrogen and halogen are called amides and acyl halides respectively. Nomenclature and structure of carbonyl group. Nomenclature. Aldehydes and ketones. Two systems of nomenclature of aldehydes and ketones are common names and IUPAC names. Common names. The common names of aldehydes are derived from the names of the corresponding carboxylic acids by replacing the suffix -ic acid with aldehyde. Position of substituents in aldehyde chain, if any, is indicated by Greek letters alpha, beta, gamma and delta, etc. The alpha carbon is one which is directly attached to the aldehydic group. In common system, ketones are named by using the names of alkyl groups attached to carbonyl group followed by the word keton. Nomenclature and structure of carbonyl group. IUPAC names. In the IUPAC system, aldehydes are named according to the following set of rules. Determine the parent compound, that is, the longest continuous carbon chain containing the carbonyl group. Replace the final E of the parent alkane with AI. Number the chain beginning with the carbonyl carbon as carbon 1. Number and name all substituents. For example, 2-methylpropanol, 3-bromo-2-methylbutanol. In the compounds in which aldehydic group is attached to the ring name is followed by the word carbaldehyde. The rules for naming ketones in the IUPAC nomenclature system are directly analogous to those for naming aldehydes. In ketones, however, the name of the keton is obtained by replacing E of the parent alkane by O-N-E and the location of the carbonyl carbon is indicated with a number. For example, 2-heptanone, 2-nananon. Cyclic ketones are named by assigning the number 1 to the carbon atom of the carbonyl group. Numbering then proceeds in a clockwise or counterclockwise direction to give the next encountered substituent the lower number. Nomenclature and structure of carbonyl group. Structure of the carbonyl group. Carbonyl carbon is joined to 3 other atoms by sigma bonds. Since these bonds utilize sp2 orbitals, they lie in a plane and are 120 degrees apart. The remaining p orbital of carbonyl carbon forms pi bond with oxygen atom. Carbon and oxygen are thus joined by a double bond. Since carbon and oxygen have different values of electronegativity, the bond between carbon and oxygen is polar. In fact, electron density around the oxygen atom is increased, which causes the development of partial positive charge on carbon and a partial negative charge on oxygen atom. Thus, the carbonyl carbon is an electrophilic and carbonyl oxygen is nucleophilic center. The dipole moments of aldehydes and ketones are quite high. The dipole moment of ethanol, propanol, and diethyl ether are 2.72, 2.88, and 1.18 diopter respectively. Preparation of aldehydes and ketones. Preparation of aldehydes and ketones. By oxidation of alcohols. The oxidation of a primary alcohol to an aldehyde. Butanol is oxidized in the presence of pyridinium dichromate and forms butanol. A mild oxidizing agent must be used in the oxidation of a primary alcohol to an aldehyde. Otherwise, the aldehyde will be further oxidized to a carboxylic acid. The oxidation of a secondary alcohol to a keton. On adding chromatic acid in isopropyl alcohol, then it forms propanone, which is a keton. Preparation of aldehydes and ketones. By dehydrogenation of alcohols. When alcohol vapors are passed over a heated metal catalyst such as silver or copper, primary alcohols give aldehydes whereas secondary alcohols give ketones. When vapors of ethanol are passed over copper, then ethanol is formed and hydrogen gas is released. When vapors of isopropyl alcohol are passed over copper, then propanone is formed and hydrogen gas is released. Preparation of aldehydes and ketones. From hydrocarbons. By ozonolysis of alkanes. Ozonolysis of alkanes gives ozonides which on reduction with zinc and water give aldehydes and ketones. Ozone gas reacts with ethane and forms an intermediate, that is ozonide, in which some zinc is mixed along with water and forms methanol and hydrogen peroxide. Ozone gas reacts with 2,3-dimethyl-2-butene and forms an intermediate, that is ozonide, in which some zinc is mixed along with water and forms propanone and hydrogen peroxide. By hydration of alkynes. When acetylene vapors passed through aqueous sulfuric acid in the presence of mercuric sulfate, acetaldehyde is formed. Preparation of aldehydes and ketones. Preparation of aldehydes. From acyl chloride, acid chloride. Benzoyl chloride on catalytic reduction in the presence of palladium on barium sulfate results in the formation of benzaldehyde. From nitriles and esters. Nitriles are reduced to imine with tin chloride and hydrochloric acid, which on hydrolysis give the corresponding aldehydes. This reaction is called Stephan reaction. Nitriles can also be reduced by diisobutyl aluminium hydride to imine, which on hydrolysis give aldehydes. Esters can also be reduced to aldehydes with diisobutyl aluminium hydride. Preparation of aldehydes and ketones from hydrocarbons. Aromatic aldehydes are prepared from aromatic hydrocarbons from the given method. By oxidation of methyl benzene. Benzaldehyde can be prepared from toluene by Attard's reaction. The reaction involves the oxidation of toluene with chromyl chloride in carbon disulfide, which gives chromium complex, which on hydrolysis gives benzaldehyde. Toluene is oxidized by chromic oxide in acidic anhydride to form benzyldene diacetate, which on hydrolysis with aqueous acid gives the corresponding benzaldehyde. Most of the common aldehydes and ketones are liquids at ordinary temperature. Aldehydes and ketones have relatively high boiling points as compared to hydrocarbons of comparable molecular masses. Lower membranes of aldehydes and ketones are soluble in water, but the solubility of these compounds in water decreases with the increase in the size of alkyl group. Preparation of aldehydes and ketones. Preparation of ketones from acyl chlorides. A Grignard reagent readily reacts with cadmium chloride to form a heavy metal derivative, that is an organocadmium compound, and magnesium chloride. The organocadmium reagents are sufficiently nucleophilic to react with acyl halides. Thus, the reaction of an organocadmium with an acid chloride is an important method for the preparation of ketones. The cadmium reagents are useful because they are too unreactive to add to the byproduct ketone, and thus the reaction is stopped at the ketone stage. Preparation of aldehydes and ketones from nitriles. Treatment of nitrile with Grignard reagent followed by hydrolysis yields ketones. Grignard reagent in ether reacts with propanenitrile, and then it forms an intermediate, and then upon hydrolysis it gives propiophenone from benzene or substituted benzenes. Treatment of benzene or substituted benzene with acid chloride in presence of anhydrous aluminium chloride gives the corresponding ketone. This reaction is known as Friedel-Crafts acylation. Physical properties. Physical state. Except formaldehyde, which is gas at room temperature, most of the common aldehydes and ketones are liquid at ordinary temperature. The lower molecular mass aldehydes have sharp, rather unpleasant smell, but higher molecular mass aldehydes and ketones are pleasant smelling. In fact, some ketones are useful in perfumery. Some aromatic aldehydes obtained from natural sources have very pleasant fragrance. Physical properties. Boiling point. Aldehydes and ketones have relatively high boiling points as compared to hydrocarbons of comparable molecular masses. It is due to the reason that aldehydes and ketones contain polar carbonyl group, and therefore they have stronger intermolecular dipole-dipole interactions. These dipole-dipole interactions are, however, weaker than intermolecular hydrogen bonding in alcohols. Consequently, boiling points of aldehydes and ketones are relatively lower than the alcohols of comparable molecular masses. Ketones are relatively more polar than their corresponding isomeric aldehydes due to the presence of two electron-repelling alkyl groups around the carbonyl carbon. Thus, boiling points of ketones are slightly higher than isomeric aldehydes. Physical properties. Solubility. The lower members of aldehydes and ketones are soluble in water. It is due to their capability of forming hydrogen bonds with water molecule. The solubility of these compounds in water decreases with the increase in the size of alkyl group. It is because of the increase in the magnitude of non-polar part in the molecule. Did you know? Formaldehyde is a colorless, inflammable, poisonous gas with a penetrating odor. German chemist August von Hofmann, 1818 to 1892, discovered it in 1867. Methanol is used in the manufacture of dyes and plastics. It can irritate eyes, mucous membranes, and the upper respiratory system. Summary. Let us summarize what we have learned. Carbonyl group is a functional group consists of carbon atom double bonded to an oxygen atom. The common names of aldehydes are derived from the names of the corresponding carboxylic acids by replacing the suffix -ic acid with aldehyde. In common system, ketones are named by using the names of alkyl groups attached to carbonyl group followed by the word ketone. Carbonyl carbon is joined to 3 other atoms by sigma bonds, and the remaining p orbital of carbonyl carbon forms pi bond with oxygen atom. Most of the common aldehydes and ketones are liquids at ordinary temperature. Aldehydes and ketones have relatively high boiling points as compared to hydrocarbons of comparable molecular masses. Lower membranes of aldehydes and ketones are soluble in water, but the solubility of these compounds in water decreases with the increase in the size of alkyl group.